Hello, let's solve this question. The following graphs represent the current versus voltage and voltage versus current for the six conductors A, B, C, D, E and F. Which conductor has least resistance and which has the maximum resistance? See, for this graph we have V along y-axis and I along x-axis. Let this be graph 1. For graph 2, we have I along y-axis and V along x-axis. This may seem to be similar or same, but it is not so. Let us figure it out, okay? So these red lines are the graphs between V and I or I and V for 6 different conductors A, B, C, D, E, F. All are straight lines and all these lines passes through the origin. So I can comfortably use the equation of a straight line, which is y is equal to mx. There is no plus c because there is no intercept. All these lines passes through the origin. Am I making it clear? Right. So for the first graph, graph 1, listen carefully. For graph 1, I will write it in this format. What is in y place? V is equal to sum m into what is in the x place? I. So V is equal to Ri. This is from Ohm's law. Okay. So this is y, this is x and R is m, the slope. So for graph 1, slope m directly indicates the resistance of the conductor. We know slope slope m is equal to dy by dx. Slope r is equal to what is dy? V is in y's place, so dy is dv and dx is di. Okay. So the initial points are 0, 0 for all the conductors A, B and C. Let us write the coordinates for all these 3 conductors. What is the x here? 4. What is y? 2. So I is equal to 4, V is equal to 2. For this graph, I is equal to 3, V is equal to 4. For this one, I is equal to 2, V is equal to 5. Okay? Is that clear? Okay. Now let us find the resistance of A. RA is equal to dVA, change in potential for A by change in current for A. So this is equal to, what is dV? 2 minus 0. 2 minus 0 by 4 minus 0, which is 1 by 2 or 0.5 ohms. RB is equal to dVB by dIB, which is equal to 4 minus 0. See, voltage here is 4, here 0, current is 3 and 0. So 4 minus 0 by 3 minus 0, which is 4 by 3, 1.3 ohms. Alright. RC is equal to dVC by dIC, which is equal to, voltage is 5, 5 minus 0, current is 2 minus 0. So 5 minus 0 by 2 minus 0 is 5 by 2, that is 2.5 ohms. Is that clear? Right. Then for graph 2, so we have same Ohm's law, V is equal to IR, but what is in the y-axis? I. So I is equal to 1 by R into V. Okay. So this is y is equal to mx. What is in x place? V. What is in y? I. So the slope m is equal to 1 by R. So for graph 1, the slope directly indicates the resistance value But for graph 2, the slope indicates 1 by r. 1 by r, m is equal to dy by dx. That means m is equal to what is in y's place? Di. What is in x place? dv. 1 by r is di by dv. Okay. So r is equal to dv by di. See, let us write the coordinates. This is 0, comma 0. Here voltage is V is 4, I is 2. For this, V is 3, I is 4. For F, V is 2, I is 5. Okay. So, RD is equal to, what is RD is equal to? dVd by dId. What is dVd? V is 4 minus 0 by 2 minus 0. 4 minus 0 by 2 minus 0 is equal to 4 by 2, which is 2 ohms. Re is equal to dVe by dIe, which is equal to, what is V? 3 minus 0 by 4 minus 0. 3 by 4, which is 0.75 ohms. Rf is equal to dVf by dIf, which is equal to, see, V is 2 minus 0. 2 minus 0 by 5 minus 0, which is 2 by 5, that is 0.5 ohms. So which is the least resistance is? Which is the least resistance? RF, which is 0.4 ohms. Which has got the highest? RC, which is 2.5 ohms. So least is RF, which is 0.4 ohms, and maximum is RC, which is 2.5 ohms. That's it. So question number 2. Lightning is a very good example of natural current. In typical lightning, there is a 10 power 9 joule energy transfer across the potential difference of 5 into 10 power 7 volt during a time interval of 0.2 seconds. Using this information, estimate the following quantities. A. Total amount of charge transferred between the cloud and ground. B. The current in the lightning bolt. And C. The power delivered in 0.2 seconds. Okay. So we'll start with the data given. Okay. So what is given is the electrical energy or the potential E is equal to 10 power 9 joule. The potential difference V is equal to 5 into 10 power 7 volt. And time interval is given as 0.2 seconds. You are asked to find A. Total amount of charge transferred, B. current in the lightning bolt, and C. power delivered in 0.2 seconds. Okay. So we'll go for the solution. So we'll start with the direct formula. Power is equal to rate of doing work or energy with respect to time. So E by T. So E is given as energy. E is energy. Energy is 10 power 9 by time is 0.2 seconds. Okay. So this comes around 5 into 10 power 9 watts. So power P is equal to 5 into 10 power 9 watts or 5 gigawatts. Okay, and the second formula is power is equal to V into I. So I is equal to P by V. What is P? 5 into 10 power 9 watt. By voltage is given as 5 into 10 power 7. So this is 10 power 2 amps. So the current in the lightning bolt I is equal to 100 amps. Okay. Power P is equal to 5 gigawatt. And third one is I is equal to Q by T. Q is equal to I into T is equal to I is 100 for the time duration of 0.2. So Q is equal to 20 coulombs. That's it. So question number 3. A copper wire of 10 power minus 6 meter square area of cross section carries a current of 2 amps. If the number of free electrons per cubic meter in the wire is 8 into 10 power 28, calculate the current density and the average drift velocity of electrons. Okay. So the data given, A is area of cross section is 10 power minus 6 meter square. It carries a current of 2 ampere. If the number of electrons per meter cube is 8 into 10 power 28, what is that? That is the electron density. Electron density N is equal to 8 into 10 power 28. This is a count. Okay. So you are asked to find the first one current density, which is J, and second one average drift velocity, which is Vd. Okay. So first one current density. What is current density J? J is equal to current by area. So this is 2 by 10 power minus 6. So J is equal to 2 into 10 power 6. What is the unit? I is amp, by area is meter square. So ampere per meter square. Okay. So then you are asked to find the drift velocity. What is drift velocity is equal to Vd in terms of I or J. What is that? Vd is equal to, I is equal to E Vd A into N. From this, Vd is equal to I by E A N. What is I? 2. E 1.6 into 10 power minus 19 into area is 10 power minus 6 into N is 8 into 10 power 28. So this comes around 0.156 into 10 power minus 3 drift velocity, so meter per second, or else drift velocity Vd is equal to 15.6 into 10 power minus 5 meter per second. Okay, that's it. So question number 4. The resistance of a nichrome wire at 20 degrees Celsius is 10 ohm. If its temperature coefficient of resistivity of nichrome is 0.004 per degree Celsius, find the resistance of the wire at boiling point of water. Comment on the result. Okay. So what is given is the conducting wire is a nichrome wire, which is basically a metal. You have to identify that. Okay. The resistance at 20 degrees Celsius is given as 10 ohms. So at temperature T0 is equal to, this is the reference temperature, the corresponding resistance R0 is equal to 10 ohm. Okay. The coefficient of resistivity, temperature coefficient of resistivity is alpha is equal to 0.004 per degree Celsius. Okay. At T naught, the resistance is R naught. At some T, the resistance is RT. Okay. So what is asked? You are asked to find the resistance of the wire at boiling point of water. See, boiling point of water is not a single value. They have to mention at what pressure. If nothing is mentioned, you can take it as 1 atmospheric pressure. So boiling point of water is 100 degrees Celsius only at atmospheric pressure. Okay. So if it is not mentioned, we can comfortably take the pressure as 1 atmosphere. So the boiling point of water is 100 degrees Celsius. So when T is equal to 100 degrees Celsius, find the resistance, corresponding resistance value. Okay. So find RT at T is equal to 100 degrees Celsius. Okay. The solution is, so this comes under the temperature dependence of resistance or resistivity. The final formula is RT is equal to R naught into 1 plus alpha into T minus T naught. Okay. You are asked to find RT. RT is equal to, what was R naught? 10 into 1 plus alpha is 0.004 into the temperature is 100 degrees Celsius. T naught is the reference temperature. This is reference temperature, which is usually or commonly 20 degrees Celsius. Okay. So this is 100 minus 20. So this is equal to 10 into 1 plus 0.004 into 80. So this is 10 into 1 plus 0.32, which is 10 into 1.32. So the resistance at T, which is 100 degrees Celsius, is 13.2 ohm. So the temperature increased from 20 degrees Celsius to 100 degrees Celsius. The resistance changed from 10 ohms to 13.2 ohms. See, for metals, alpha is positive. That means the graph between resistance or resistivity and temperature is a linear variation, positive. Okay. So for metals, see, you are asked to comment on the result. What do you comment? See, it is not just like that. You can solve, find the answer and go. You are asked to comment on the result. They'll give you 1 mark. So for metals, as temperature increases, resistance increases. Okay. Alpha is positive. So remember, alpha is negative for semiconductors. For semiconductors, if temperature increases, resistance decreases. Okay, that's it. So question number 5. The rod given in the figure is made up of 2 different materials. Both have square cross sections of 3 mm side. The resistivity of the first material is 4 into 10 power minus 3 ohm meter, and the of second material has resistivity of 5 into 10 power minus 3 ohm meter. What is the resistance of rod between its ends? Okay, shall we start? Okay, right. Let this be the first material and this be the second material. Okay. So the length of this first material is given as 25 centimeter and the length of the second one is 70 centimeter. Okay. Both have square cross sections. This is the cut section, which is a square of side 3 mm. What does that mean? This is 3 mm and this is 3 mm. Okay. So shall we write the given data? Given length of first material is 25 centimeter, which is 0.25 meter. Length of the second material L2 is equal to 70 centimeter, which is 0.7 meter. Okay. Resistivity of the first material. Resistivity is rho 1 is equal to 4 into 10 power minus 3 ohm meter. Resistivity of the second material is 5 into 10 power minus 3 ohm meter. Okay. Find the equivalent resistance between the ends. Okay, let this end be A and this end be B. Find the resistance between R, A, B. Okay. So the equivalence is, this is resistance 1 and this is resistance 2. Okay, this is A and B. R1, R2. So it looks like they are connected in series. R1 and R2 are in series configuration. Okay. So what is the formula first for resistance? R is equal to, in terms of rho A and L, rho L by A. So R1 is equal to rho 1 L1 by A1. R2 is equal to rho 2 L2 by A2. What is the area? Area is equal to 3 mm by 3 mm. In meter, A is equal to 9 into 10 power minus 6 meter square. Okay. So substituting the values, R1 is equal to, what is rho 1? 4 into 10 power minus 3. What is L1? 0.25 by area 9 into 10 power minus 6. Okay. So this comes around 111.11 ohm. R2, substituting the values, R2 is equal to 5 into 10 power minus 3 into L2 is 0.7 and cross-section area is the same, 9 into 10 power minus 6. So this comes around 388.8 ohm. RAB or R equivalence in series combination is equal to R1 plus R2, which is 111.11 plus 388.8. So this is 499.99. Therefore, R equivalence is equal to around 500 ohms. That's it. So question number 6. 3 identical lamps, each having a resistance R, are connected to a battery of EMF epsilon as shown in figure. Suddenly the switch S is closed. Calculate the current in the circuit when S is open and closed. What happens to the intensities of the bulbs A and B and C? Calculate the voltage across the 3 bulbs when S is open and closed. And D, calculate the power delivered to the circuit when S is open and closed. Okay. So the circuit is given as, this is a EMF source. So current is drawn in this direction. Okay, this is conventional current. So it flows through, when S is open, it flows through A, B and C, and then the circuit is getting closed. Okay. So since switch S is open, no current flows through this branch. Like when it comes here, no current flows because the circuit is still open. Okay. So we are solving it as two cases. First case, S is open, and second one, switch is closed. Okay. Right. So we start with case 1 where switch S is kept open. Okay. So in this case, it is like the current flows through A, B and C, which means there are three resistors connected in series. These are loads. When current passes through these loads, there exists resistances. So there are three resistances connected in series. Let this be the EMF source. This is A, B and C. Okay. This is I EMF. This is RA, RB and RC. We know that all the resistance are same and is equal to R. So in resistors in series, the current through all the resistors are the same, but the voltage gets divided, right? So this is VA, this is VB and this is VC. Okay. So for series connection, equivalent resistance R equivalent is equal to R1 plus RA plus RB plus RC, which is equal to 3R. So current I is equal to V by R equivalence. V is epsilon by 3R. So IA is equal to IB is equal to IC is equal to epsilon by 3R. This is when the switch is kept open. Okay. So this is one current. Second, intensity of glow. So I is the same for all the bulbs and resistance are also the same. Therefore, all the bulbs A, B and C glow with same intensity. Okay. And the third one is calculate the voltage across each bulb. Okay. So voltage V is equal to I into R. So VA is equal to IA into RA, which is R. I was like epsilon by 3R into R, which is epsilon by 3. So VA is equal to VB is equal to VC is equal to epsilon by 3. Okay. Fourth one, power delivered to the circuit. Power PA is equal to VA IA, which is equal to, what is VA? Epsilon by 3 into IA is epsilon by 3R. So this is epsilon square by 9R. VA is equal to VB is equal to VC, IA is equal to IB is equal to IC. Therefore, PA is equal to PB is equal to PC, and that is equal to epsilon square by 9R. So this is when S is open. When S is closed, case 2, S is closed. Okay. So when S is closed, okay, this circuit is closed. Current is drawn from this EMF source. It flows through A and B and it comes to this point. Okay. So at this point, it can flow through this. Now these are two branches connected to this junction. But when the switch is closed, it creates a low resistance path. It creates a low resistance path compared to this. When the current flows here, the resistance here is more compared to this path. So current always prefers low resistance path. that is short circuiting. Okay, if you want more details, I can post a separate short video on short circuiting. Okay, so since current prefers this path, no current flows through the bulb C. IC through C is 0. So now if you want to calculate the current flowing through A and B, current is equal to I is equal to V by R equivalence. Now there are only two resistance connected in series. R equivalence is equal to R1 plus R2, which is equal to 2R. I is equal to V by 2R. V is epsilon. So epsilon by 2R. So from this, IA is equal to IB is equal to epsilon by 2R, which is greater than the previous case, epsilon by 3R. Okay. Second, intensity of glow. So intensity of glow what happens? Since more current flows through A and B, so the intensity of glow of bulb A and B increases from the previous value. Okay. Third one, voltage drop. VA is equal to VB is equal to I into R. I is epsilon by 2R. So into R, that is epsilon by 2. So VA is equal to VB is equal to epsilon by 2 and VC is equal to 0. Here IC is equal to 0 and bulb C does not glow. And power, fourth one, PA is equal to PB is equal to V into I. V is epsilon by 2 into I is epsilon by 2R, which is epsilon square by 4R. So I am writing it here. For closed condition, PA is equal to PB is equal to epsilon square by 4R and PC is equal to 0. Okay. So initially power is epsilon square by 9R. Now it is epsilon square by 4R. That means total power increases. Here the question is, does the power delivered to the circuit decrease, increase or remain same? We know that the total power increases. Okay, right. So you can check for the answers here. Okay, that's it. So question number 7. An electronics hobbyist is building a radio which requires 150 ohm in her circuit, but she has only 220, 79 and 92 ohm resistors available. How can she connect the available resistors to get the desired value of resistance? Okay, so what is given is, see, the resistors available with her are R1 is equal to 220 ohm, R2 is equal to 79 ohm and R3 is equal to 92 ohm. Okay, but what is required is 150 ohm. So what we do is, normally if we have 3 resistors but our requirement is different, you have to use the available resistors in different combinations, could be either series or parallel or a combination of both series and parallel, so that you get the required resistance of 150 ohm. Okay, so first you start with all the resistors are connected in series. But we know that if the resistors are connected in series, the equivalent resistance is larger than the maximum of the individual resistances. So when resistances are connected in series, R equivalent in series is equal to R1 plus R2 plus R3, okay, which is 220 plus 79 plus 92, which comes around 391 ohms, which is not what she wants. Then you try connecting all the resistances in parallel, okay. So we know that when the resistances are connected in parallel, the equivalent resistance is smaller than the smallest of the individual resistances. The smallest of the individual resistance is 79. So when these resistances are connected in parallel, the equivalent resistance is going to be less than 79, which is also not the required value, okay. But let us try. In parallel connection, 1 by R equivalence is equal to 1 by R1 plus 1 by R2 plus 1 by R3, which is 1 by 220 plus 1 by 79 plus 1 by 92, okay, which comes around 0.028. 1 by R equivalence is 0.028. R equivalence in parallel connection comes around 35.62 ohms. Again, it is not what she wants, okay. R equivalence when all the resistances are connected in series was 391, so that is of no use. So we are not going to connect all in series, not even all in parallel. So we have different combinations now. What I am going to do is connect R1, R2 in parallel and R3 in series, okay. Fourth option is going to be R2, R3 in parallel and R1 in series, okay. Or what you can do is fifth option, R1, R3 in parallel and R2 in series, okay. So we'll start with third one. Let this be R1 and R2. These are connected in parallel and this is connected in series, okay. This is 220 ohms, this is 79 ohms and this is 92 ohms. So these two R1 and R2, this is R3. So I'm going to find an equivalent resistance. This is R12 parallel, this is R3. Then I'm going to find an equivalent resistance where R12, 3 are in series, okay. So for parallel configuration of R1 and R2, 1 by R equivalence is equal to 1 by 220 plus 1 by 79. So this comes around 0.0172. So R equivalence is 58.12. This is R equivalence of 1 and 2 in parallel. Then R equivalence of 1, 2 and 3 is equal to 58.12 plus 92. Okay, these two are series, no? So directly we can add these two. So it comes around 150. R equivalence is equal to 150 ohm. So what we have done is, there is a parallel combination of 220 and 79. So the answer is given as parallel combination of 220 and 79. and this combination is in series with 92. So what you get is the equivalence is 150 ohms. This is 58.12 ohm and this is 92 ohm. Okay, that's it.